All right, my friends, I think I'm going to go ahead and get started. Hello and welcome. I'm glad you all came back again for another episode of General Hospital. I don't know what soap opera you guys watch, but anyway, I have a couple announcements before we get into some new stuff today. First things first, today is the last day to sort of easily add or drop any class, really. But specifically as it pertains to this class, if you just want to pretend like this never happened, you don't want to get a W, you don't want to get anything on your transcript with 250B, today is the day you have to do it. So if you're thinking about, you're on the fence, not sure if you want to take the class, you've kind of seen the workload, it's definitely going to keep coming hard and heavy. So if this is not what you're up for, you might want to talk to me today about it, but you do have to get yourself dropped by midnight tonight if you just want to get out. In terms of adding, there were 3 of you, I believe, on the wait list. Tarek, you should have gotten an email a very short time ago. Jacob, I think you also would have had one. And is Brian here? You should have had one as well. So the math department should have emailed you and given you an ad permit. So you should be good to go, but you have to take care of that permit by midnight tonight. If you just sit on it and it goes into tomorrow, all bets are off. Then you have to have me sign a bunch of paperwork and the dean has to sign it and you have to pay a fee and all that stuff. So make sure you work on it today. If you have any trouble with that, let me know. Okay. So, and if you didn't get the email, let me know because they should have done that. By now, I think my grader has finally had a chance to look at the first couple of assignments that you had. I just wanted to explain in case it wasn't clear. A couple of people were asking me how their papers were graded. So all of my assignments are out of 20 points for homework. So you'll have some number over here, whatever it is, but it's made up of 2 parts. And what those 2 parts are is my grader will give you some points just for turning it in, just for doing a complete submission of your assignment. So that might be something like, I think he usually uses about 5 or 6 points. So you might have had something like this on the top of your paper. This just means you got credit for turning it in. The rest of the 20 points, so in this case, it would be 14. That's going to be based on my grader picking specific problems to check. And if he takes off any points, he should tell you why. Like he should give you some comment. If for any reason you don't know why you lost points or you disagree with the grading of your homework, you can come bring it to me. I can always overrule the grading, or I can tell you what I think was the problem or whatever. So, but you'll have some number of points out of 14, and then it just gets added together to a total out of 20. Okay. Keep in mind, my grader's not paid a whole lot. He doesn't have a huge amount of time. He's not going to be grading that many problems. It's not going to be like super amazing detailed feedback. If you really want the best possible feedback, feel free to come talk to me. You can come to my office hours. And I am posting the solutions to the homework in the folder in Canvas that says homework solutions. As we submit these assignments, I've been publishing those for you guys to be able to see. So even if you got a 20 out of 20 on your homework assignment, it doesn't mean that your assignment was perfect, right? Because my grader may not have looked at everything. So it's not a bad idea to follow up and just check the full solutions that I've presented. And if there's anything you're not sure about, you're always welcome to talk to me about it. Okay. Speaking of homework, we have another assignment that's due tonight at the end of the evening. I have a lot of office hours today, so feel free after class, you can stop by and see me, or after my later classes. So at 5:30, I'll be downstairs pretty much all evening, except for a dinner break, which I usually take at about 7 o'clock. So other than being gone for about an hour or so, I should be around. There are some problems already on the board over here. During the break, if you want to add anything else to that list, you can. I don't promise to do all of those. I'll probably do that first one, though, the number 32, because that's a little bit of a theoretical problem. But I will try to save a little bit of time to look at some of those problems. And if I don't get to all of them, you just have to come talk to me about them, and I'll be glad to help. Okay, so that's kind of my preview. Does anybody have any questions about either the enrollment stuff or the homework grading so far? So far, so good. By the way, our first midterm Can I talk about that yet? Our first midterm is on September 25th. I believe that's a Thursday. So that's a little over 2 weeks from now. It will cover chapters 1 through 3, 1, 2, and 3. We've already finished chapter 1 completely. We're currently in the middle of chapter 2, and we should finish that for sure this week. So that will leave us just with chapter 3 to do next week. Chapter 3 is the shortest chapter in the book. It will only take us less than a week, or maybe about a week to do it. It's very, very short. So pretty soon I'll be pointing you to some things in Canvas that you can look at to help you get ready for it. It's a little early at this stage, so I don't think I'll bother you too much, but just have that in the back of your mind. We do have a test coming up. Oh, and you all want to get extra credit for this test coming up. So if you haven't stopped by my office yet, either in Zoom or in person, just for a quick little 5-minute chit chat, please do that. I will, if you do that, I will write your name down and I will then make extra credit available to you. There's going to be an extra credit quiz coming up that you can earn points towards this midterm for before you even have to take the test. So that'll be kind of nice, and it'll be a good way to study. But you have to do the little 5-minute intro in order to be eligible for that. Okay, make sense? All right, sweet. If there's nothing else, boy, I hope I remember what I was talking about before I went on my 4-day backpacking trip. Last Thursday, wow, feels like a lifetime ago to me. We were talking about linear systems. This is really what chapter 2 is all about. And there's kind of 2 different ways now that I've talked to you about representing the linear system. The first way on the left, I'm calling it approach 1, is really just the bare bones, lay it out there, write out your equations. Okay. And so you can just lay out the equations, write them all out. And ultimately what we will end up doing, and I've put a little space here to add this at the bottom, we will ultimately have an augmented matrix that we associate with that system. So I can write that, guys. I can just put basically my matrix of coefficients on the left, and then there's a bar, and we have our little right-hand side vector B that you just attach vertically as a column on the right. And that's just laying it out kind of in the most basic way that you could, right? Writing out your system. So that's approach number 1. On Thursday last week, though, I talked about multiplying matrices together, this sort of funky way where we do dot products of rows of a matrix, the first matrix with columns from a second matrix, right? We do these dot product calculations. Using that, we can actually write our linear system a little bit differently. We can get our hands on the coefficient matrix. We can get our hands on the right-hand side vector, which is what B is. And then we can lay out our unknowns as a column vector, right? And if we do that, I'm going to put something down here on the board as well. If we do that, we can write this linear system, guys, as a matrix multiplication. A times X equals B. So you should have this already in your notes. Remember, this is just a recap, right? This is just a summary of kind of where we left off at the end of last week. You guys with me? So I can either just lay out all of the data into this augmented matrix, or I can represent my system this way. A times X equals B. The goal, as we've discussed, right, is to solve the system. We would like to solve our linear system for the unknowns. In this case, it's pretty clear. It's the X vector is the unknowns. And looking at the AX equals B, we would love to solve for X by dividing by A. We talked about that last week. That's actually not allowed. We can do tons of things with matrices, but we cannot divide by a matrix. So on Thursday, I'm going to come try to salvage some way of solving for X when it's been put into this form. Okay, so we're going to come back to that later. It's going to turn out we're not always going to succeed. Well, we actually know that already. Not every linear system is consistent. There are systems that just don't have solutions. So we're not always going to be able to solve for this X, but we like to try. Okay, on Thursday, I'll talk about that idea of sort of getting rid of the A to isolate X. Okay, what I want to do though today is come back over to this first approach, this bare bones, lay down the numbers into a big matrix thing. And I want to talk about how you can solve the system if you render it this way. Okay, and we're going to be using this all semester long, guys. So I'm glad you're here today because this is kind of important. Okay, so I am going to discuss how that works right now. Is everybody good? Are there any questions on this recap? Anything that over the weekend people have been stewing over, not quite comfortable with? I think some of these homework problems, right? They give you the system and say, write down the matrix of coefficients, write down the right-hand side vector, write down the augmented matrix. Super quick, super easy. You don't even really have to show any work. You just write down the answer to some of those problems. It's pretty straightforward. Okay, well, if everybody's good with that, I am going to take a stab here at the next section. So the first three sections of chapter 2, we kind of did those last week as a whirlwind discussion. The title I'm going to give for section 2.4, guys, is EROs and REFs. I'll explain what those acronyms stand for in just a minute. But to kind of get this ball rolling, I have 3 remarks about this process of solving our linear system that I'd like to get into your notes for you, okay? And this is not spelled out exactly this way in the book, so it's definitely worth getting this down or at least taking a picture of these notes because I think this is a good way to think about it. So the first one is, and let's see if you agree with this remark, a linear system is easy to solve. It is easy to solve by something called back substitution. So this is a phrase you'll hear when you're talking about solving linear systems. So a linear system is easy to solve by back substitution if it is in a so-called triangular form. If it is in a so-called triangular form. I think I'd like to write down an example to show you what I mean by this remark. Let's suppose that I give you this system here. 2x minus 3y plus z equals 6. And then 4y minus z equals 8. And then z equals 4. So there's an example of a linear system, and I think you can kind of see why we say that this is in triangular form. There's kind of a triangle shape to the the left sides of these equations. And does everybody agree with my comment here that it would be easy to solve this system for the unknowns? I think you probably have all done something like this. You start at the bottom and say, oh, I already know what z is. Z is equal to 4. Then I would take that value, plug it into here, plug in 4 for z here, then I can solve for y. So if z is 4 and we plug that into this equation, we can solve for y. I believe y would be equal to 3. And then we could take both the y value and the z value, plug them in up onto the first equation, and solve for x. And I think I'll save you the mental arithmetic of solving for x here. It's not very difficult. It comes out to be 11 over 2. Does everybody see how I do that? I'm not showing a lot of work. Basically, you start at the bottom and work your way back up to the top, and you solve for x, y, and z. Now, guys, I want to get some good habits developed right away in this class when we're solving systems. I don't want your answer to look like that. When you're actually writing down your solution to your system, you should write, I'm going to put it here. You should write it, just do this with braces. So you bring in a little brace notation. I want everybody to do their solutions this way. And then we make slots where we spell out what x, y, and z are. So 11/2 for x, 3 for y, and 4 for z, and then we end the brace. So this is the way we would formally want to write our solution in good notation. Okay, so don't just leave a bunch of scattered back substitution chicken scratch all over, right? You need to actually kind of put in a nice final answer here. Okay, everybody comfortable with that? So that is back substitution of a system in triangular form. Easy to solve. Easy to solve for the unknowns. Okay. Good so far? All right, let's do number 2. My second remark. I said there's 3 remarks here. What is my second remark? Well, this is actually the most important one. No solutions to the system. No solutions to the system are gained or lost. No solutions to the system are gained or lost if we perform these operations. Okay, and I'm going to put a colon there because I'm going to make a list right now. We won't gain anything and we won't lose anything if we do certain things. So let me tell you what these operations are. There's 3 of them, so I'll label them with A, B, and C. So the first operation is called permuting, and I'm going to denote it as P sub ij. So you're going to want to adopt these notations. Pij just means permute equations I and j. So for example, P12 would just switch the order of the first 2 equations. P23 would switch the second and third equation. Guys, I think you would all agree, you don't need to jot this part down, but I'm just going to show you. I think you would all agree that this system right here has the same solutions as this one did. I mean, after all I did was switch the second and third equation. I permuted them, right? So by the way, here I have something that's not really a triangle, right? So if somebody handed me this system, I might say, if I just permute the second and third equations, I can get it into triangular form, and then it's easy to solve by back substitution, right? So you can take something that's maybe not given in triangular form to begin with, and you can use this operation to make it triangular. Okay, so that's kind of the idea. Let me give you another one. So another operation where we don't gain or lose anything is if we multiply. I'm going to write this one as M sub I of K. This is my notation. And this one is multiply the ith equation by K. But before we leave that thought, I do want to point out that K must be not 0. Okay, so again, if we come back over here to this system that we started with, I think you would all agree that if I multiplied the third equation by 10, M3 of 10, which would make this the third equation, that my solution has not changed, right? Z is still equal to 4, therefore y is still equal to 3, and x is still equal to 11 over 2. This is a perfectly safe operation. We don't gain or lose anything by doing that. Now, obviously, if I multiplied through by 0, then I would lose that entire equation, and now I got problems, right? Now I definitely don't know how to solve for z right away. So it has to be a non-zero number. Anyway, so that is the second operation. Make sense? Okay, hopefully I'm not saying anything too crazy. This third one is the hardest one to kind of get your hands around, but with some practice, I think you'll become more comfortable with it. This is the adding operation, and this has a double subscript, so it's A sub ij of k. And this one stands for adding. So what we do here, guys, is we add k times the ith equation to the jth equation. So we take one of the equations in our system and we mentally multiply it through by k, but we don't actually change that equation. Notice in this operation, guys, I don't actually do anything to the ith equation. It's the second subscript, the j. That's the equation that feels the effect of this operation. We take k times the ith equation and add it to the jth equation. We are not going to gain or lose anything if we do this one. So any of these three, in fact, they are all safe operations to do to your system. These things collectively, I need a little room here. These things collectively are called elementary row operations. Which of course is abbreviated EROs. So that's part of where the title of this section comes from. Those are called EROs, elementary row operations. They are safe operations to perform on your linear system. When I use the word row here, it sort of suggests that I'm talking about a row of a matrix. In these first two remarks, I didn't say anything about matrices explicitly, but I'm going to add that now as my third remark. Okay, and this third remark is an easy one. It's not what I meant to say. The number 1 and number 2 above the two remarks I just made, which are about linear systems, can equally well apply to the rows of the augmented matrix. So these apply to the rows of A sharp. So when I talk about the row operations, I'm thinking of it kind of in the context of having a matrix. And by the way, I am going to have a matrix, right? Because I'm going to take my linear system and I'm going to put it into A sharp, just directly. Once I have A sharp, I can go to town with these EROs and hopefully bring it into a nice triangular form that's easy to solve. And in fact, that is really the process that we're going to describe here, guys. And we're going to do an example in just a minute, but let me describe this process to you. Here is what we're going to do. We are going to use EROs, my friends. We're going to use EROs to convert A sharp, which is the augmented matrix that I'm starting off with, into, well, you probably think I'm going to write the word triangular form, but actually, as it turns out, you can't always make it into a perfect triangle. Here I gave you one where it was really pretty nice, but it's actually not always a perfect triangle. There's a fancier word I need to give you here, which also comes up a lot in linear algebra, namely that we're going to convert A sharp into what is called row echelon form. Row echelon form. So that is where, by the way, the REF in the title of this little lecture comes from. Row echelon form is the sort of the more generic substitute for what I called triangular form back here in the beginning. I lost my word triangular form, but that was what we tried to do here. I better tell you what row echelon form actually is as a definition, and then we are going to do examples. Okay, everybody good so far? So let's just do a quick definition. And then I think we'll be good to go. So the definition is a matrix is in row echelon form if it's in row echelon form if two things are true. Two things are true. The first thing is any all zero rows are at the bottom. So if there's any rows that are all zero, those are going to be laying down at the bottom. Well, what if I have a row of zeros that's not at the bottom? What can I do? Homan? Permute it so it is at the bottom. Exactly. I have my ERO. I could permute whichever equation or whichever row that was all zeros, just permute it to the bottom, and you'll satisfy this first rule. So for a row echelon form matrix, any rows that are all zeros should be stacked at the bottom, and we have a way of achieving that by doing permutation, permuting as appropriate. Okay? The second part of the definition, and this is the last part, is that for all other rows, the first non-zero entry. So for all of the other rows, the first non-zero entry, which is by the way, there's a word for that. It's called a pivot. So a pivot is going to be the first non-zero entry. Must be a 1. Okay, now I'm not done yet, but I want to pause for a second. What if it's not a 1? What if my row starts off 0, 0, 0, 7? Go ahead, Homan.
Multiply by 1 over 7.
Right. If my first non-zero entry is a 7 and my requirement is that it is a 1, I can multiply that row, whichever the I value is, whichever row it is, I can multiply it by the reciprocal of what it is. So if it was a 7, I could multiply that row through by 1/7 and turn it into a 1. Easy peasy, right? So it becomes a pivot when it's a 1. So it must be a 1, and there's a little bit more here, and occurs to the right. It occurs to the right, guys, of the pivot in the row above. It occurs to the right of the pivot in the row above. Just to make sure everybody's following this, let me just draw like a picture of this. So what would be like a row echelon form of a matrix? So I like to use this notation. So you have your matrix A, you do these EROs to it to try to get it to look like the row echelon form requirement here. And how does that look? This is kind of just an example. Just kind of give you a rough feeling for what it looks like. Right, what you're gonna have, guys, is some big matrix like this. If you have any rows of all zeros, those are gonna be stacked at the bottom. Maybe you have a couple of them. Any all zero rows go way to the bottom of the matrix. And then for all of the other rows, the first non-zero entry has to be a 1. And guys, I am going to more or less require you to do this, even though the book doesn't. When you have a pivot in your matrix, please put some kind of I like to use a little diamond around it or circle it or whatever. It's really important that you make it very clear where your pivots are positioned. So the first non-zero entry is a 1, and then actually what comes after that could be any numbers. It actually doesn't matter what's coming up on after that. Okay. And then in the next row, the pivot must occur to the right of the pivot in the row above it. So on the second row, there could be also a pivot, but it must be to the right. Now, it might be a ways to the right. Maybe it's not until you get way over here. You could have several columns that don't have any pivots at all. That's perfectly possible, right? And then maybe on the next row, we have to go even further to the right to get to our pivot, right? This is kind of what it would look like. And then maybe the next one, this is just an example. It's just gonna show you roughly how this is gonna end up looking. So it's kind of like a warped triangle. This triangular form I was proposing over here is now kind of a little bit off. It's a little bit skewed because of, the pivots do not just follow a nice, perfect straight line. They can be kind of staggered like I showed here. But I claim that you can use these three EROs to always put your matrix into this form. Once it's in this form, we're gonna solve it easily by back substitution. So we need to practice this a little bit, but that's the game plan. That's the game plan. Is everybody with me? Let's try an example. On this first example, I just want to practice the EROs. I'm not gonna have a linear system here. I just want to get the EROs written down. So let's just take A to be the following matrix: 2, -1, 3, 4. And then 1, -2, 1, 3. And then 1, -5, 0, and 5. Let's take that matrix, and what I would like us to do is we're gonna take this matrix. Notice I'm not putting an augmented bar or anything. I just want to practice with this raw matrix. But I would like to find row echelon form of A. REF of A. So we have a matrix A, and my goal here, right, I'm gonna try to find a row echelon form for it. Okay? Watch this closely, take good notes, because the way I write this down is the way I'm gonna want you guys to do it as well. All of this is gonna be practiced on Friday's homework, the very next homework assignment, okay? So let's get going on a solution here. Can you guys all, maybe I should, let me draw it over here so I have enough room. It takes a little bit of space. We're gonna be doing these EROs, guys, these elementary row operations, till the very last day of the semester. This is not gonna go away. So might as well really get a handle on it, the sooner the better. Okay, so yeah, so what we're gonna do, the way I like to do this, I'll start my solution here. I can't break that camera. I have 1,000 pictures on it from my hike. I took so many pictures, so I've got to be careful not to topple it over. Yeah, so here's the way I like to do it. I like to just start with my matrix. I won't rewrite it all out again. And anytime I'm going to do an ERO, I'm going to use a little twiddle. It's like this little sideways S. And then I'll have a new matrix that is the result of doing that operation. So I'm sorry, I'm going to make you look back and forth here for a minute. Looking at this matrix, does anybody want to suggest an ERO that I could use to try to start bringing it to look more like row echelon form? Yes. Is it Pablo?
Yes.
Yes, please.
So that.
Okay, you have 3 choices. Subtract is not one of them. Your choices are permute, multiply, or add.
So, add row 2 times -1 to row 1 in order to get 1, and then.
You want to get a 1 up here, right?
Yeah.
The whole goal is to get a 1 in the upper left corner. So what Pablo suggested is I could take -1 times the second row and add it to the first row, which would get the job done and it would be fine. Is there an easier way to get a 1 into the upper left corner, Brian?
We can permute the first.
I think, Pablo, your idea is great, but what Brian is saying is easier to get a 1 by just permuting. So maybe we just permute the first 2 rows. Let's do that. So if that's what I'm gonna do, then I'm gonna put next to this twiddle, guys, I'm gonna put that notation, P12. And what that means is I'm gonna switch the first 2 rows. So the second row is now listed first. The first row is now listed second. And we're not really touching the third row right now, so I just recopy it the way it was before. I am going to circle my pivot or put a diamond, which is what I like to do. I'm gonna put a diamond around that pivot that is now in the correct spot in the top left corner of the matrix. Okay, now what I know is that the pivots have to go down and to the right. That means that what numbers do I have to have below this pivot? Look at our model over here. Below every single pivot, what do I see? Nothing but zeros, right? So below a pivot, you must have all zeros. Does anybody want to help me turn this 2 into a 0? I'll give you a hint. By the way, I'm not even going to mess with the first row. It is so good. We're so happy with that. But how do I get a 0 right here? I can do it right now. This is where, guys, this third ERO turns out to be really important. It comes up probably the most often. I'm going to use this adding operation. I'm going to take a multiple of one of my rows and add it to that second row. And what I could see is if I want to turn this 2 into a 0, I need to take -2 times the first row and add it to the second row. That would be written as A12 of -2. So let's now, guys, we can do this in our head. You don't have to write out all of the mental math that you're doing. I have to take all 4 numbers from that first row, and in my head, I'm going to multiply them by -2 and add that to the second row. So -2 times 1 is -2. I add that to 2, it becomes 0. -2 times -2 would be 4. I add that to -1 and it becomes 3. -2 times 1 gets added to 3 and becomes 1. -2 times 3 becomes -6. It gets added to 4 and it becomes -2. So you have to go all the way across the whole row doing that ERO. Remember, guys, we're not gaining or losing anything, right? All the solutions are being preserved through this process. So I have created a 0 right here. Now, I'm going to give you a little time saver trick, if that's okay, which is that I already know what I want to do next, which is that I also want to get a 0 there. So we can actually do that in the same breath. We can do this in the same step. I don't need to like do another twiddle and do another, write it all out again. How can I get a 0 in the bottom left corner? Kind of going back to where we came from. How can I turn this 1 into a 0? Sorry, just a second. Go ahead. What was your name again, by the way? Right, yeah, please. Okay, so it's actually the adding operation. I love it. Adding operation from the first row to the third row of -1. Guys, just to be very clear, to figure out what ERO to use right there, I'm literally just looking at these 2 numbers. The rest of the matrix, I don't even care. It's just that number. How am I going to use that number to 0 out that number? That's all it is. So I have to take the negative of the first row and add it to the third row. Let's go all the way across the matrix and do that. Negative of -2 is 2. Add that to -5, I get -3. -1 added to 0 is -1. -3 added to 5 is 2. So I actually just did 2 EROs in one step. But don't get carried away with that. I have seen people try to do this. They'll take the matrix and they'll say, oh, I'm going to add A12 whatever. Oh, and I'm also at the same time, I'm going to multiply row 2 by 5. And then I'm going to permute row 2 with row 3. Then I'm going to permute row 2 with row 4. And I'm pretty dizzy by now. And in fact, I can't keep track of it in my head. When you permuted rows 2 and 3, was that before or after you added 5 times the first row to the second row? And, you know, which order did you do these in? And did you really do it all in your head? Probably not. Please do not go crazy wild about doing many steps at once, especially if they are tangling up the rows. Right? These two EROs really don't interact with each other. You're doing one thing that affects the second row and you're doing something else that affects the third row. That's perfectly cool. Nothing wrong with that. Okay, so anyway, just wanted to warn you about getting too crazy with too many things at once. Now that I've got the matrix in this form, does somebody want to suggest another ERO step that I could use at this point? What was your name again?
Jacob,
Jacob, please.
you just add row 2 to row 3.
Okay, A, so that would be written as A of 2, 3 of 1. So you're gonna take 1 times the second row and add it to the third row. I like it. So we leave the first row the same. Actually, when you do this operation, you don't change the second row. It actually stays the same. But we're adding the second row to the third row, and that's quite nice. We get our row of zeros at the bottom. Okay. By the way, I already know that this is going to become a pivot. Technically, to be a pivot, it has to be a 1, according to my rules over there. A pivot has to be a 1, but I already know that this 3 is going to be where my pivot is by the time it's all said and done. But I'm not quite there yet. What other ERO do I still need? Somebody want to throw out an idea here? Say one more time. For what?
The second row.
The second row. Multiply the second row by 1/3. That would be M2 of 1/3. Okay, so exactly. So the first row stays the same. The second row gets multiplied through by 1/3. And of course, the third row stays the same. This would be it. This would be it. Is everybody with me on that? We good? I got a question for you though. Is this the only right answer? So remember, this is the matrix we started with. Did we have to do exactly all of those EROs? Exactly the way I did them here? I don't think so. I don't think so. There would have been other ways to get a 1 in the upper left corner. Maybe instead of permuting the first 2 rows, what if I permuted rows 1 and row 3? Then my first row would have become this. And all the way through the calculation there, my first row would have been not this first row. Okay, so there can be lots of right answers. There's actually, can anybody think of another way of getting a 1 into the upper left corner without permuting? Ryan? I could have said, my very first step, you don't need to write this down, but my very first step could have been to multiply the first row by 1/2, right? And then just whatever is here. Do you guys think this would have been a good thing to do? I know how painful this homework is going to be. It's one of the homework number 5 is kind of tedious. But if you want to make it less tedious, can I give you a little piece of advice? Do not put fractions into your matrix any sooner than you absolutely have to. Here, of course, we ended up with fractions, but at the very end when it was easy. If you put fractions into this matrix right from the start, then when you start doing the Aij operation, you're going to be adding fractions to fractions. And you guys all love to add fractions in your head? They don't have the same denominator, it's even more annoying. I don't think you want to do that. So, you know, this would not be wrong. This would not be wrong, but it would also be annoying. It would not be my best choice for how to do it. Okay. I do want to make this remark though. The remark is that the row echelon form of A is not unique. Okay, there are many correct answers. There can be many correct answers. That's nice in a way, but it does come with a downside. The fact that there's lots of right answers means that if you want to check your answer in the back of the book. Remember, by now you probably all know that the odd numbered answers are in the back of this book. But the back of the book is only going to have one of the possible correct answers, of which there are many. So although there are many correct answers, you may come up with one that's not the same as the back of the book. So if you're checking answers, don't assume that your matrix was wrong just because it's not what's in the back of the book. Okay, because there are many correct answers. However, although there are many correct answers, there is one thing that all correct answers will have in common. And while I'm erasing the board, I want you to think about what that might be. There's one thing that, so, all 30 of us could have come up with 30 different row echelon forms here, depending on what EROs we chose to do, right? We could have 30 different correct answers, but my question is, what would be maybe something that would have to be common to all of them? Does anybody have a guess what I'm looking for here? Is it Edgar? Yeah, please.
They're all upper triangles?
They will definitely all have to have the row echelon form rules. That's definitely true. Because if it's not an upper triangular form, then we're not done yet. Then we have to do more EROs. What else? Does anybody think they might have an idea? What was your name one more time?
Max.
Max, please.
They're all gonna start with the one.
They're all gonna have to start with a 1. That's also part of the definition over here. Okay, so they're definitely all going to fit this description, but I'm thinking of something, just looking at the final answer here, above and beyond just that it meets the rules of row echelon form. Is there something else? Yes.
Are all the pivots gonna be in the same place?
The pivots, now we're getting closer. Yes, the pivots is what this has to do with, and they're in the same place. Actually, I want something even more fundamental about the pivots. Yes.
Does it have to do with the free variable? Or-
I haven't talked about free variables yet. I'm coming to that, coming to that. But I want to go back to pivots. The thing that is actually, the thing I'm fishing for, apparently my fishing expedition is not quite working out. That's okay. Is that the number of pivots must agree. All 35 of us would get the same number of pivots, in this case, 2. There's 2 pivots. The third row does not have any pivots. The number of pivots. So I'm going to call this a remark, which is that all row echelon forms for a matrix will have the same number of pivots. And because it's a common number, it therefore leads to a definition, and this is a big word in linear algebra that always shows up. I'm going to put it as a definition here, guys. It's called the rank of the matrix. Okay, so the rank of A, by definition, the rank of A is the number, I'm going to use a pound sign for that. It's the number of pivots in any row echelon form of A. The rank of a matrix is the number of pivots. Right? So in our example above, so guys, what is the rank of the matrix that we just worked on in our example? 2. I've got 2 pivots, exactly. So if you're checking answers with your friend, make sure that at least, you might not have the same answer, but you should make sure that you at least got the same number of pivots, the same rank, if you will. Does that make some sense? This is actually a fairly deep remark. It's not something I'm gonna stop and like go into a full justification of right now. So we just take this one kind of as a freebie, that any 2 correct row echelon forms will always have the same number of pivots. This is the same rank. And by the way, you usually cannot just glance at your matrix. Take a look here, guys. You usually cannot just glance at the matrix and tell me what its rank is going to be. It's not just the number of rows that you started off with. This matrix had 3 rows. to start off with, but as it turned out, the process of doing EROs zeroed out one of those rows and left me with only two pivots. It left me with only two pivots. So that's kind of the story on that. Everybody comfortable with this? This takes a little bit of practice. I will tell you that the students come to my office hours and they've got 2 pages worth of EROs written all out. They're like, what's going on? It usually shouldn't take that long, right? Usually you can pin down a row echelon form with 4, 5, 6 steps. It shouldn't be, if you're on step number 12 and you still don't have it yet, my guess is that you maybe could pick a better set of EROs to get there. But it does take practice. And everybody always hates the homework for this section because it is kind of a lot of, tedious mental math here. It's just the way it is. I do promise you though, that I will lighten up a little bit about it once I feel comfortable that everybody's able to do this easily. We'll start to sort of make things a little simpler. Let me just see where I'm at. I think. Well, so we're missing one thing. We've practiced the EROs, but we haven't fully done the process yet. The full process is that we want to actually take our linear system, which is A sharp, and bring that into row echelon form in order to solve our system. So that's what I need to talk about next. I think we're about halfway through the class. Why don't we take a 10-minute break now? I'm going to put a problem on the board during the break, and then we'll pick up and we'll practice how to use EROs to solve the system. Well, let's take a 10-minute break and get some water, walk outside if you want to, stretch your legs, whatever you need to do, and then we'll come back. All right, I'll see you in about 10 minutes.
About adding class, do I just go to enroll?
Oh,
Yes.
so you would have gotten an email.
Yeah.
I think you should be able to go to enroll and use the kernel. If you can't get it to work, could you go to the math department's office, which is MH 154?
Right.
Because I don't really know what it looks like on your side.
Gotcha.
Yeah, let me know if you have any trouble with it.
I do have one problem, and I don't know if this is fiscal, you might know, but I have a class overlap. And it didn't tell me that was a problem when I enrolled the first time, but now it's saying that I can't enroll next to the overlap. But the final schedules are different. They're
So
not-
what is the other class?
Physics.
So when is that class?
It starts at 11:30.
Oh.
So it's like 20.
So what are you planning to do?
I would like to just keep both of them. I already took
But I mean-
physics 226. I'm retaking.
So is your other professor okay with that?
I mean.
So you're going to show up
I am sure
30 minutes later.
about it.
I don't know. It's obviously not a problem for me because, but if the system isn't gonna let you enroll for that reason, I can't solve that problem.
Okay.
You can go to the math department and see what they can do with that. But yeah, unfortunately, I don't have a good answer for this.
Okay.
Yeah, okay. Hey, Jacob, yeah.
Yeah, so I noticed that when you get told us that you want us to be writing it like this.
Yes.
I know like when I would do it, at least when I did elementary row operations, like
Yeah.
it was just to like arrow and then it's like, oh, row 2, row 1.
Yes,
Muted and stuff.
I know what you're talking about. I
Mhm.
don't want you to use that. I
Okay.
want you to adopt mine. I meant to say that actually, and I
Mhm.
forgot to.
No,
So
no, you're good.
thanks for bringing that up. Yeah.
Okay, so but you want us to write it like
Yes,
M or A.
for
Okay.
now.
Okay,
I
that's
will
fine.
get, I will get much more soft on it
Mhm.
after I'm convinced everybody knows what they're doing.
Okay, sounds good.
Yeah, great.
Can I see the
Hey, Reed.
Facebook?
Yeah.
I'm supposed to put more than 9.
Yes, go ahead and open that up. Sure. Uh-huh.
Take a look at board.
Just a second.
You're good.
Number 4, you said?
Yeah, what you need to do there is, you just literally you plug in S, where you see X1, and then plug in T, sorry, plug in S minus 2T, where you see X2.
No.
Plug in 2S plus 3T, where you see X.
Oh, it's that.
So T, and just make sure that they all do cancel out. So you're just like checking. This just writing down the coefficient matrix, the right hand side vector, and you want the matrix, it's just writing.
Oh, okay.
Did you write this on the board?
Might have been Jose or
Oh,
Trevor,
okay, no worries.
but yeah.
Yeah, no problem.
Okay, thank you.
Yep. Oh, nice. Yeah, it's fine.
You take the door.
No. He literally is kidding my remote. Like it's literally right next to you. Yeah, he's literally. It's quiet. Break the server between. Stomping around. I'm setting my lease for next year. Okay. It's so good. Number 3.
Wait, this is the odd one out.
Not doing it again? They might take up again. They can't pay their. So boring. She was like, sure.
Saw that when I was looking.
That's crazy. So me and that's all we're for. So like you walk upstairs and it's like a camera that you see here. There's like a count. Like it looks there. There's my bathroom separate from my room.
What's on the bottom? You're already excited.
Nice, you know. That's
Yes.
and they're read. I'm just looking at it.
Okay.
What was this? We're doing to the
This is actually really
about
good.
investigating. Yeah.
Jake.
There's like an outside area where we well, I can't.
Kind of title thing.
Yeah, we get a dining room table, that's kitchen and everything first. The room is moved down. Well, that's like that's just based on the six. Jason. He has like a sounds. There's the stairs. There's the Upstairs is a council that has that water. I was just doing about these. So like I don't want to call it that. Yeah. And then they move out. What's up here with this? It's the couch, like the table, and everything. It's like a little. Close that intro.
When they're facial cats, because when they're sitting back.
I guess it's what if it needs a second. This is like I would say couch, and I just think I think it's about going to this TV like monster. That's really cool. And then there's that. That's absolutely. And it's they're like like a moss. Yeah. What's that? I have no idea. It is. It's not that big, but it's nice. Still a walk. Yeah. You're gonna make you decide right now. Yeah, there were some, you know, I haven't decided for the end. It's gonna be a lot of stuff. They're like resign.
Alright, guys, I think I've got just about everybody back here. It's hopefully been about 10 minutes. Does anybody have any questions so far about anything we've talked about today? This seems pretty. You know, it's actually not that super high powered abstract, but it's also kind of tedious. You just gotta be. Don't try to do this stuff like when you're really tired or when you're trying to do 3 other things at once. Because you know what is so frustrating is you make a mistake in the first ERO you do, and then it carries through the whole calculation to the end, and then you realize, oh, I made a sign error or something silly like that in the first step, and then you have to like go do the whole thing again. So try to do these problems. This is for Friday's homework. Try to do them when you're feeling good, when you're feeling fresh, and when you can focus on it. You'd be more likely to get it all correct if you do that. I want to take those raw EROs that we just learned about and actually use them now to solve a system of equations. And the technique that we're going to learn right here is called Gaussian elimination. Okay, so this is a standard process in linear algebra. It's very computational. The concept of it's pretty simple, but we just have to be very careful. So what we're going to do, guys, to solve this system, which I've got on the board, first of all, notice that there are only 3 equations, but there are 5 unknowns. So now you know why I don't really want to talk about triangular form anymore, because this isn't really going to look like a triangle shape. It's going to be more like row echelon form shape that we talked about before the break. So the first step to this, guys, is always to just put it into the augmented matrix. Okay, and by the way, this is similar to problem number 9 on section 2.3. They give you a system of equations, I believe, and they just ask you to write down the augmented matrix for it. So I'm not going to do number 9. I'm just going to do this and ask you to follow the same model for that homework problem. So the augmented matrix, we just grab these coefficients, right? The numbers that are in front of our unknowns. We're going to add that far right column. So we put a bar there with the 0. Okay. And then the second equation, same thing. Just grab the coefficients, lay them out into the second row. And then I'm going to do the same thing on the third row. I'm just grabbing all of the coefficients and laying them out like so. Now, when you write down the A sharp, of course, you don't see the unknowns anymore. The U, the V, the W, and so on, they're not actually written down here in blue. But what we need to always remember is that those unknowns are attached to the scalars from a particular column. So U, V, W, X, and Y are lined up with these columns like so. All right. So what our process is we're going to use EROs right now to convert that A sharp into row echelon form. Okay. So I'm gonna get my twiddle out and start doing EROs on this, okay? Does anybody want to suggest maybe a good ERO that we could start with here? Maybe somebody I haven't heard from yet. Pablo, appreciate it. Trevor?
Row 1 plus row 2. Or no, row 1 plus row 3 to get a 0.
Okay, so you're gonna add, you're doing adding of
Yes.
row 1 to row 3 to get a 0 down here. I like that, but I'm actually gonna do two things at once. Okay, so let's do two things at once. I'm gonna do A 1 3 of 1. Now, what is that? That's taking 1 times the first row and adding it to the third row. Incidentally, guys, during the break, somebody came up and asked me if you have to use these notations. The answer is yes. Okay, I know that different books will write it differently sometimes, but let's stick with the notation from the book that we're using so that we can follow it very clearly. So I'm gonna add 1 times the first row to the third row. That does not actually change the first row. But it does change the third row. I'm going to add the first row to the third row and I'm gonna get a 0 and then a 0 and then a -1 and then a 1 and then a 0 and then a 3. Make sure that if I'm going too fast that you slow me down to check. I'm just adding everything in the first row to everything from the third row. Now, is there another ERO that we might do at the same time? Jakob?
Just do A2 negative.
A1, 2 of -2. So he's just looking at these two numbers. And he's saying, how can I turn that 4 into a 0? Well, you can take -2 times the first row and add it to the second row. That's exactly what I'm gonna do. So I'm gonna make a 0 there. If I take -2 times everything on the first row and add it to the second row, I should get 0, 0, and then 0. And then -1, and then -3, and then -5. Okay. I want to point out, some of you might be wondering, well, wait a minute, I thought the first thing we should do is get a pivot in the upper left corner, which would be a 1. Right now, that upper left corner is not a 1, but you know what I'm really trying to do? Avoid fractions. That in order to get a 1 here, right, I could multiply by 1/2, but then you'll have all these fractions right away and have to live with them for the rest of the whole solution. So what we're realizing kind of is that, yeah, we can eventually turn this into a 1, but let's not do it quite yet, right? I can even sort of see a game plan here. I'm gonna circle where the pivot positions are right now. You can see they're not aligned correctly for the way they're supposed to go down and to the right, but we're getting there, you know, getting quite a few zeros into the matrix here, okay? Can somebody suggest another ERO to do from here? Read.
From you 2.
I love it. So the pivots are not aligned properly here. I need to get they need to go down and to the right instead of down and to the left. So if we just do P2, 3, that would be great. So I'm gonna leave the first row the same. 2, -3, 1, -1, 1, augmented with 0. The third row is now going to become the second row. Okay, so I'm just recopying the third row into the second row, and then the second row is going to become the third row. So 0, 0, 0, -1, -3, and -5. Okay, that looks pretty good so far. Am I in row echelon form yet? My pivots are all going down and to the right. What's the only thing wrong with my pivots right now? The pivots must be a 1. They must be a 1. Well, all 3 of them are not 1s, but I can actually, now here's another place where I would feel comfortable with you doing all of them at the same time. Let's multiply the first row by 1/2, and we'll multiply the second row by a -1. And we'll multiply the third row by a -1. Let's do those all together in one step. That shouldn't be too confusing. So the first row becomes 1, and then -3/2, 1/2, -1/2, 1/2, augmented by 0. The second row just has basically a sign change. So 0, 0, 1, -1, 0, and -3. And then the third row also has just a sign change. So 1, 3, and 5, like so. And that is a row echelon form for our matrix. It's not the only correct answer. By the way, just as a quick little check, can somebody tell me what's the rank of this matrix? I erased the definition. The rank is the number of pivots, and we see 3 of them, right? So this would have a rank of 3, just as a little side comment. Let me just write that down. Rank equals 3. We're not going to see today so much why the rank is so important, but we're going to be talking about the rank for a long time. So it's something to kind of get comfortable with. Now, guys, remember, no solutions to our system have been gained or lost through any of the stuff in blue, any of the solutions. I still have my unknowns here that are lined up with these columns just as they were when we started. If I want to, I can now take this matrix and rewrite the equations from it. We don't actually normally need to do this, so we can just leave what we have here and go on to the next part of the solution. But just so everybody is clear, we have still 3 equations here. U minus 3/2 V plus 1/2 W minus 1/2 X plus 1/2 Y equals 0. That's one equation. And then the second equation would have been W minus X equals -3. And then the bottom equation would have been X plus 3Y equals 5. Okay, now what I just wrote down there in red, guys, we don't really need to write it out, but I just wanted you to see it kind of in print, in color. The solutions to this system in red are exactly the same, no more and no less than the solutions to the original system that we had before. But somehow, having it in row echelon form, which is what this matrix is giving me, is going to make it easy to solve. What was the first remark? Easy to solve by back substitution. Let's do it, because we're not done yet. We still have to do the back substitution part. Now, here's the thing that's a little weird. You remember the one we did earlier? The one we did earlier was super easy. We had the bottom equation was z equals 4. And then we had, what was it, 4y minus z equals 8. And we could easily like plug in starting from z, go to y, go to x. Here, when I start at the bottom equation, I'm like, well, what do I do with that? Right, I mean, x plus 3y equals 5, well, that doesn't tell me what y is, and that doesn't tell me what x is. In fact, there's tons of choices. X could be 5 and y could be 0. Or x could be 8 and y could be -1. There's lots of right answers. So in fact, what I'm going to recommend, we've got our pivots. I'm going to circle the pivots on these variables. Okay, and I'm going to make a quick little, I guess I'll call this a definition. Okay. By the way, guys, think about how many solutions you think this system has. Okay, how many it has. That's an interesting question. The definition, guys, the variables corresponding to the pivots. So in this example, that would be the U and the W and the X, right? The variables that are pivoted variables, these are called leading variables. Okay, so I have 3 leading variables in this example, which are the ones that correspond to the pivots, the U, the W, and the X. The other variables which in this example would be what? V and Y. The V and the Y. These are called free variables. That's Pablo, what you were trying to talk about earlier. Now we've got it on the board for ourselves. Every variable in our system is either a leading variable or a free variable, depending on whether it has a pivot attached to it. And guys, the word free on that name is quite appropriate, because what it is that I can freely choose the value of that variable. I can choose y to be any number I want, and I'll be able to then solve for x. And then once I know what x is, I'll be able to solve for w. And then when I go back from there, v will also be free, but from there I'll be able to solve for u. You see that? How many solutions do you think this system has? Infinitely many, because exactly right, because we have a free variable. Because we can choose y to be any number that we want and v to be any number that we want, we have tons of solutions to this system, right? So let's do this, guys. Let's let y be equal to t, which is a free variable. So I'm going to write the word free there and try to remind myself that y is really free. Now, people will sometimes ask me, well, what's the t? What are you doing with the t? There is no t in the problem. I like to use r, s, and t as free variables always, so that I will always be in the habit that when I am using letters like r, s, and t, that I will remember that, oh, those are representing variables that are free. They can be any number that we want, okay? Technically, some other mathematician might have a beef with that and say, why don't you just leave it as y? Why do you have to change it to some other letter? I just like to get in good habits of continually like rewriting free variables using the same letters over and over and over again. After I've done that for 15 weeks of a semester, I'm going to be pretty well trained on that. So that's why I do that. But once I know what y is, then I can solve for x using this back substitution from the bottom. X will be, well, it's 5 minus 3y, but I want to write it, guys, in terms of the free variable again. So I'm going to change it to 5 minus 3t. Okay, so that's what x is. And then w is also a leading variable. Notice that if I solve for w in the middle equation, it becomes x minus 3. So x minus 3. But again, I'm not going to leave it as x. I want to rewrite it using the free variable. So I take 5 minus 3t and I subtract 3 from it. Well, that'll leave me with 2 minus 3t. So w becomes 2 minus 3t. Okay. Then the next variable that so we're doing back substitution, but the next variable that we come to is v, which is free again. So I'm going to let v equal r, and I'm going to label that as another free variable. So the v and the y are the free variables. So I'm using, as I said, r's, s's, and t's. I don't like s quite as well because it looks like a 5, but people get mixed up with that. So I usually will start with r and t as my free variables. Okay, then guys, what is u? But u is another leading variable, so I can solve for it. It's going to be 3/2 of v minus 1/2 of w plus 1/2 of x minus 1/2 of y. Does everybody see that? If I solve this first equation in red for u, I have to move all of those terms to the other side of the equation. And would I be happy leaving it like that? Probably not, because otherwise I wouldn't be asking you this. I want to write it always using the free variables. So my u should be written in terms of t and r. Right now I've got v, w, x, and y. So what I'm going to do is replace in what all these expressions are. I am going to leave out the sort of boring algebra of that. So I'll just say equals ... And I'm just going to tell you what it comes out to be, if that's all right. What you're going to get is 3/2. Where is it here? 3/2 plus 3/2 of r minus 1/2 of t. So I'll just put the word check that. It's maybe not obvious just glancing at it that that's what it would be, but that is the final expression for u. So, are we done? Is that the way I'm gonna wanna leave the answer with all the chicken scratch, kind of all disorganized, spread out all over my paper? No, no, no. I talked about this earlier, right? We have this nice little solution notation. So let me show it to you again. What we do, just to remind you, we get out our braces. Okay, and then I'm gonna start making slots. The first unknown goes in the first slot. So the u variable was 3/2 plus 3/2 of r minus 1/2 of t. That's the u variable. And then comma. The next variable is v, and that was just r. Comma. And then w, which was 2 minus 3t. And then comma. X is 5 minus 3t. And then one more comma. And then finally what y is, which is t. Make sure you list them in the correct order. U, and then v, and then w, and then x, and then y. And guys, we're gonna add a little more snazzy notation here on this one, because we're actually using some free variables. I am gonna put a colon here. This is just some mathematical notation that I want you guys to be familiar with. The colon just stands for the words such that. Okay, and then after the colon, we're just going to list our free variables. So the r and the t. And then there's another fancy math symbol that looks kind of like a little lowercase e. But it stands for the words belongs to. Math is just a language, right? Just to get used to the notation. And then I'm gonna put my big real numbers notation. That you probably have seen in calculus, the big scripted R thing. And so then we can close our brace. Okay, does that make some sense? So this system has infinitely many solutions. You give me values of R and T, I can write down 5 numbers, U, V, W, X, and Y, right? So you can just imagine there's billions of choices for R and T. As soon as you give me those 2 numbers, I'll be able to fill in what all 5 of these slots actually is and make a solution. And all 35 of us could come up with 35 different solutions to that system. And in fact, there's really infinitely many. Unlike the one we did earlier, right? The one we did earlier, you remember this one this is way back at the start of today's class? We just had one single solution to that first triangular system that I showed you in the first remark of the day. So this was a one solution scenario. So if I give you a system of equations, it might have one solution. One solution, you'll know it because there's no free variables there, right? There's no R, there's no T. Basically what that meant was that every single column had a pivot. There were no unpivoted columns. See, these unpivoted columns are what are giving you the free variables. Do you think there's any other possible outcome to your linear system? We could have one solution. We could have infinitely many solutions. Does anybody think there could be a different number of solutions that we could end up with? Say it again. No solutions. I think so. Well, how would that play out in the Gaussian elimination? Let's just do a quick example. Maybe I can convince you. I think I showed you this before. Solve if possible. And then my system was what? X plus Y equals 1 and X plus Y equals 2. Let's write down something we know doesn't have a solution. I would just like to show you how the Gaussian elimination plays out when you're in sort of a no-win situation. If this is your system, guys, let's just see what could possibly go wrong with that, right? What could possibly go wrong? Let's just check it out. Let's just play dumb. Let's say I don't recognize whether there's a solution or not. Let's just put it into our augmented matrix here. 1, 1 augmented with 1, 1, 1 augmented with 2. This is the A sharp, right? So you got your augmented matrix there. The first row is already good to go with your pivot. It's in the right position and everything. I need to, of course, make the numbers below the pivots always have to be 0, because the pivots have to go to the right. So what ERO would you suggest I use right here, guys? I'm not gonna change that first row, but I need a 0 there. How do I get that 0 where that 1 is right now? Yes, and what was your name again? Is it Ryan?
Ryan,
Yeah, please.
you multiply the second row by the negative of the top row.
So are you gonna do permute, multiply, or add here? That's, I guess, those are your 3 choices. Your 3 EROs are permuting,
You're adding,
you're adding from which row to which row?
the top row to the bottom row.
First row to the second row, exactly, and of what multiple?
Negative.
There we go. So I'm gonna take -1 times the first row, I'm gonna add that to the second row, yeah? Well, if I do that, if I take the negatives of everything in the first row and add them to the second row, I should get 0, 0, and then 1. And let me circle this pivot here. So there's my row echelon form, and what is bizarre is I have a pivot in the far, far, far right column here. If I now go back and rewrite these as equations, let's see, what would they be? The first row is still just x plus y equals 1. What does the second row say? The second row says 0x plus 0y equals 1. And you look at that and you say, ha, no way, right? 0x plus 0y is 0, and 0 does not equal 1. This is impossible, right? This is impossible. And so this is a case of no solutions. And I can basically tell you when you will have no solutions is exactly when there is a pivot that has drifted all the way into that augmented column on the far right, right? So this is since a pivot is in the far right column. That's really what's going wrong here. That's really what's going wrong. Okay. So I've got one linear system that had one solution. I've got another linear system that had infinitely many solutions, thanks to the free variables. And now I've given you a system that had no solutions. So the number of solutions to a system, I guess I should be calling this a remark. The number of solutions, it could be 0, or it could be 1, or it could be infinity. And we've seen all 3 examples. Could there be anything else? Could there be a system that has exactly 17 solutions? Or exactly 25 solutions? Some other fixed number, you think? The answer is no. This is it. Every linear system will have either 0 solutions, 1 solution, or infinitely many solutions. And how do you know which one it is? It all comes down to the pivots, right? If there is a pivot in the far right column, you'll have no solutions, right? If you have pivots that leave free variables, then you'll have infinitely many solutions. And if you have a system where there's basically every variable is pivoted, no free variables, then you have exactly 1 solution. There are 3 possible outcomes. 3 outcomes of Gaussian elimination. I'm sorry to write this so far down on the board, guys. If you're in the back, feel free to stand up. If you Google that online, 3 outcomes of Gaussian elimination onto YouTube, Google it online, guess whose pretty face you're gonna see? You've all subscribed to my channel by now. Yes, I made a video basically showing all three outcomes of Gaussian elimination and talking through it. So if you want to see another nice example of it, it's not very long. It's like 10 minutes or something. I recommend you check that out. Unless you already understand it, in which case we're good to go. But it's definitely something I want everybody to be understanding. Okay, how are we doing here? Everybody with me? Yes, please, Jessica.
For the infinitely many solutions,
Yes, like this one.
if you could just like take a glance at it, if the number of equations compared to the amount of variables, if it's less, if the equations are less than the amount of variables, would it always result to infinitely many?
So what if I have this? That's a good question. He's asking me if I have more unknowns than I do equations. That would seem to suggest lots of solutions because you've got so much freedom and flexibility. But don't write this down, guys. But what if my second equation had been this? So, I have tons of unknowns, not very many equations to satisfy, but even so, you can see just looking at this, that this will have no solutions. You can't generally just glance at these things and say, oh, based on the shape of the augmented matrix, I'm gonna know how many solutions there is. So that's a really good point. That's a sign of somebody who's thinking about this a little bit more conceptually. But it turns out that you really can't just glance at these systems and be able to tell that. Great comment though. Any other questions on this? Are so good? Okay, so for Friday, everybody's gonna practice these EROs a lot. And if you get frustrated, you can come cry in my office. And I'll try to help you out. Keep in mind, you should never have to do more than just a handful of EROs. If you're like going in circles, doing EROs forever, it probably means that a trip to my office would be a good idea. I'll try to streamline it for you, give you a little bit of a quicker way to approach it. Okay, I'm gonna save 10 minutes to take those homework questions, but I find myself with just a little bit of time. So I am going to start that second approach thing that I mentioned in my recap today. Remember what that was? Instead of doing all this Gaussian elimination and the A sharp and the EROs and row echelon form, why not just put our linear system in this form using our funky matrix multiplication that we learned last time? And why don't we just figure out if we could find some way to divide by A to solve for the unknown X? That's what I'm going to talk about. So we'll just get started on this. I will have to come back on Thursday to finish, but this is the next section. I know I'm going pretty quickly through chapter 2, but this is something called inverse of a matrix. It's called inverse of a matrix. So I'd like to start the conversation today, and then we'll really dive in full blast on Thursday. Let me start with a definition. The first thing about the definition is that the matrix that we're kind of going to be playing with here is, I'm going to call it capital A, and we're going to let it be an n by n matrix. So we're already basically screwed if this matrix isn't just square size. So if my A is here, the A is 3 by 5. So everything I'm about to say in this whole section about approach 2 won't apply if your system has a coefficient matrix that's not square. So this idea of trying to get rid of this A and throw it on the other side, I already told you it's not going to work all the time. And now you can see it's actually not going to work a lot of the time. Because if my matrix is not a square size, I can't even get to the first sentence of my definition here. Right? But if this is the case, if A is a square matrix, then if there is a matrix B, and this one would be also n by n, such that A times B. Okay, let's pause. This is an n by n matrix multiplied by an n by n matrix. So that does work. You can do that multiplication. And if that turns out to equal the identity matrix, let's see, do we remember this from last week? This is the matrix that has ones on the main diagonal and zeros everywhere else. The idea behind that was that this is the matrix that when you multiply it by anything, it just leaves it alone. So it's like multiplying by the number one. It just is unaffected by what you multiply it by. Okay? And I'm gonna add one more thing. It turns out it's not actually necessary, but I'm gonna put B times A here as well. We learned last week that the order that you multiply matrices in can make a difference. So I wouldn't want to assume that A times B has to be the same as B times A. It turns out, however, that in the case when A times B is equal to the identity, B times A will also have to be the identity. So you don't actually have to check that part. It's just good to know. So if there is a matrix B such that A times B is also equal to the identity, then we call B an inverse of A. B is an inverse of A in that case. Okay. And A would be an inverse of B. They would be inverses of each other. And kind of, I mean, guys, if the identity matrix is kind of like the number one, then this is kind of sort of saying like A and B are almost like reciprocals of each other. It's like 7 times 1 7 gives you 1. So it is kind of like a way of, if I have a 7 and I want to cancel it out, I would use a 1 7 to turn it into the identity. I'm all thinking about how to get rid of this A and get it to the other side of the equation. Okay, but let me ask you a question. Here. I'll just ask it as a question for the notes. Okay. The question is, oh, I'm so sorry. I forgot. I need to say one more thing before I get to my question. My bad. I get excited. Can you tell? I actually really like this stuff. So if B is an inverse of A, then we say that A is invertible. I meant to add that to my notes there. So in that case, A is invertible. One of the most important things about a matrix, if it's a square matrix, n by n, a very important question is it invertible or not? So in this case, it would be. If we can find another matrix to sort of cancel it out with, to make A times B equal to the identity, then these matrices are inverses of each other and they're invertible. Okay, so that we have. So now I'm going to ask my question. Can a matrix A, which is n by n, have 2 inverses? Would it be possible for A to have 2 different inverses potentially? Just a little bit of a conceptual question. There will be a homework problem about this eventually for you, but I'm going to tell you the answer right now, which is the answer is no. You might not have a real strong feeling for that, but that turns out to be the answer. And what I would like to do right now, guys, is show you a proof. You might have noticed we've come a long way from the Bernoulli differential equations and the doing integrating factors. We haven't seen a derivative all day. We haven't seen an integral all day. I haven't seen a lot of calculus all day. One of the things we're going to be doing in 250B, guys, is a little bit of theoretical perspective on some of the material. And anytime you see the word proof on the board, it means I'm about to show you like conceptually or sort of rigorously using sort of math standards, let's just say. I'm going to actually really try to convince you that a matrix cannot have two inverses. Is there a, just strategy wise, you have an idea how you would prove that there is not two of something? It's really something that math majors have to do all the time. If you're more into the engineering stuff, maybe you don't see this very every day. Yeah, home?
Try to get two inverses.
Yeah, let's suppose that there were two inverses. Suppose that A has two inverses, and what I'm going to try to convince you is actually those two inverses were the same. So that you really did not have two different inverses, right? So for this proof, I'm going to suppose that B and C, they're both n by n, are inverses of A. Yeah, I'm going to suppose that there's two of them. So what would this mean? This would mean, so this means. Okay. We don't have a lot more to go today, guys. But by the way, these theoretical proofs are usually very short. Unlike the page of EROs that you have to write out to solve a linear system, this is all the space I need for this problem. Okay, what this means, if B and C are both inverses of A, it means that A times B is equal to the identity, which is equal to B times A. And it also means that A times C is equal to the identity, which is equal to C times A, right? Both of those would be true. So A and B are inverses of each other, and A and C are inverses of each other. So C and B are both inverses of A. Well, now what I'm going to convince you, I hope, and this is the part you're going to need for your homework assignment, for this is actually now getting to next week. But I'm going to try to show you, and this is what you will need to find in your notes for one of the problems from 2.6. I'm going to try to show you with the little steps filled in that B is equal to C. If I can do this, if I can convince you of how to fill in this gap, that will show that there are not two different inverses for A. This is all being done abstractly. Notice there's no numbers here. I'm not like playing with an example. This is like very, very general that we can make this argument. So here it is, guys. You ready? I love this. We're going to start with B. And we've been saying all along that if we just multiply by the identity, that's like multiplying by 1. So I'm going to just put an identity next to that. And then I'm going to take that identity and I'm going to notice here, I can take that identity and replace it with AC. So let's take that and put AC there. We learned last week also with our properties of matrices that parentheses when you do multiplication doesn't matter, right? So I could just as easily have done it this way. I could put the I'm not changing the order of anything, but I'm redoing the parentheses with the B and the A together. What is B times A equal to? Identity, right? Okay, so I put that in, identity times C. Can you tell I've done this before? Exactly the right amount of space. Identity times C, which is equal to C. So there you go. There are not two different inverses for A. There is only one. And if you tried to make two inverses of A, you could actually show that they were the same, in fact. So here's my basically punchline from that. So we conclude that if A is invertible, if A is invertible, it has one unique inverse. It has one unique inverse denoted. Ready for the notation? We're going to just write it as A to the -1 power, which is kind of an expected notation. However, you will never see me do this. and I hope I will never see you do this. Somebody every semester always does. I always have to get out my red pen. It's awful. Just make sure it's not on your paper, right? We never divide by a matrix. So this is kind of our substitute or our next best thing we can do is we have this a to the minus 1 power. So let me write down the quick application here. And then we'll go look at the, we'll spend the last 5 minutes looking at the homework that's due tonight. We won't be very long for that. The application, guys, is that if we are given a linear system, A, which is n by n, times x equals b, where A is invertible. If A actually has an inverse. So if I take my linear system here and I want to solve for x, right? I'm not going to divide by A, but what I am going to do, if A is invertible, that means that it has this unique inverse A to the -1. I'm going to take my system and I'm going to hit it on the left on both sides by that inverse. So I'm going to have A inverse times AX equals A inverse times B. Yeah? And what is A inverse times A? One is the right concept. I mean, the A inverse times A is basically the B is like the A inverse. A inverse times A is equal to identity is what I really wanted to hear. Identity. So that actually, I'm gonna give myself a little more room here. Right? So that's just identity times X equals A inverse times B. Yeah. But identity times X, as we know, the identity is like multiplying by 1. It's just X equals A inverse times B. There's how you can solve for X if there's an A inverse at your disposal. Yeah. Good enough? You probably have lots of questions. I have to give you my little soap opera moment, so you'll come back on Thursday. The one question you would have, I'll just say, I'm not going to write it down. I want to go to the homework, but I'll just very quickly say, one question you're going to ask me is, how do I know if A will have an inverse or not? Like, how do I know if A is actually invertible? And then the other question going along with that is, well, if it is invertible, how do I find the A inverse? How do I come up with this matrix that I can multiply A by to get the identity? These are great questions. So I love making people wait 48 hours for the answer. I don't have time to answer it now. So we'll leave it at that, but you can see that we are motivated, right? We're motivated to want to find A inverse so we can solve our system using that equation. Okay, I'm going to leave it at that. I've got about 3 minutes to quickly talk about the problems on that sideboard there. And I do want to talk about that first one especially. So give me just a minute to erase. Any questions though? Okay, we've gotten a lot done today. This has been super. Let me do problem 32 from 2.1 with you. I'll write it down in case you haven't had a chance to look at it yet. 32. I think my grader likes this problem. Every semester he seems to grade this one. So you can just all copy it down. And then if you all lose points on it, it's gonna be really bad for me. So we'll see. So it just says show. Show is just another word for proof. Prove that show that an n by n symmetric upper triangular matrix is diagonal. The book has some kind of a hint there. Let's just not do that. We'll just write it down here. Let me just, well, to do this problem, you had to have reviewed what all these words mean. Symmetric just meant that A transpose equals A, right? We learned that last week. If you switch the rows and the columns of the matrix, it doesn't change. Upper triangular, that just means that, you know, everything below the main diagonal of this square matrix is 0. Right? If those two things are both true, then your matrix is a diagonal matrix, meaning it only has entries on that main diagonal. So let's just write it. This is just a paragraph. This is just a couple sentences. What we're going to say is, since A is upper triangular, I'll start with that. Just write it as a paragraph. Since A is upper triangular, all entries below the main diagonal are 0. That's just kind of what this is showing. All the numbers that are below the main diagonal is right there, yeah? Everything below that main diagonal is 0. However, if the matrix is also symmetric, then remember that that diagonal serves like a mirror. So whatever you're seeing below the diagonal has to be the flipped reflection of what's above the diagonal. So I'll add that now. Since A is also symmetric, the entries above the main diagonal are also 0. Yeah, well, that's what a diagonal matrix is. If all the entries below and above the main diagonal are 0, then the only place where you can have numbers that are not 0 is right on the main diagonal. This is a diagonal matrix. So the entries above and below are both 0. So this is a diagonal matrix. Yeah, does that make sense? You just write it as a quick sentence. Okay, in 30 seconds, I can do 2.2 number 1J, super fast. So I'm gonna steal the 30 seconds to do it, just because somebody put it on the board, and I wanna make sure you all get this right. They give you a bunch of matrices on this problem. I'm not gonna write them all down. They give you A, B, C, D, whatever, all those matrices. And then they ask you to find a matrix K. They call it K, such that K transpose plus 3A minus 2B is equal to 0. They're assuming it's a 2x3 matrix, doesn't really matter. And you're just solving that for K. I bet before I can get this board erased, you can isolate that K. Just move everything to the other side. Right, so you just take this thing. Just move everything to the other side, except I'll leave the K transpose on the left side. So I'm gonna put 2B on the right, and I'm gonna subtract 3A on the right. So that's K transpose. If that's K transpose, then to get K, all you gotta do is, remember, if you take the transpose of the transpose, you get back to the original matrix. So K transpose transpose would just be K. This is the answer. They give you this matrix and this matrix, so you need to write them down. Multiply by 2, multiply by 3, subtract, all that jazz, and you can get the answers real quick. Okay, so that's how you do 1J. I think I'll leave it at that because I am out of time. If you've got questions on 2.3, you can also come to my office hours. So I will see you guys later, either in Zoom or in person. I would love to talk more. Hope this all made sense. See you guys soon.
Thank you, Professor.
Thank you.
Are you going to your office tonight?
I am headed straight there.